Hi everyone, this is Zihao Xu. Today I'm going to present our work, Domain Indexing Variational Base, Interpretable Domain Index for Domain Adaptation. This is a joint work with Guangyuan Hao, Hao He, and Hao Wang. Domain adaptation mainly addresses the cross-domain generalization problems in machine learning models. Typically, we'll assume that in the source domains, we have source data x's and source labels ys. In target domains, we only have target data xt. Our goal is to predict target labels yt within target domains. Recent studies have shown that using domain indices can significantly boost domain adaptation performance. To fully appreciate the magic of domain indices, we should first understand what are domain indices. In general, a domain index must meet the following requirements. First, it is a real-value scalar or vector. Second, it must uniquely identify a domain. Different domains should have different domain indices. And finally, it should represent the domain semantics, much like a word embedding. The distance between different domain indices should indicate the relationship of different domains. To illustrate the concept of domain indices, let's consider a gender classification task. In this task, we aim to classify gender based on face shots. We have two source domains, which mainly consist of young people, and two target domains, which mainly consist of older people. In this case, we can use the average age as the domain index. It satisfies all the requirements of a domain index. It is a real-value scalar, uniquely identifies the domain, and represents domain semantics. We further demonstrate how to use domain index to improve domain adaptation. I will take continuously indexed domain adaptation as an example. It mainly uses domain indices in two key areas. First, it takes domain indices as the input of the encoder. Second, the discriminator and the encoder play a min-max game centered on the domain indices. The discriminator tries to predict the domain indices beta based on the middle feature z, while the encoder tries to fool the discriminator by removing all domain-related information in the feature. This min-max game enforces the independence between the domain indices and the feature, which makes feature domain invariant and thus improve the domain adaptation performance. So far, we have explored how to use domain indices in domain adaptation. However, there is a challenge. Domain indices may not be available. This severely limits the application of such indexed domain adaptation method. A natural question is motivated. Can we infer the domain indices directly from data? And the answer is yes. There are two major advantages of inferring domain indices. First, it improves interpretability of domain adaptation. This is because domain indices can shed light on the domain relationship. Domains with similar domain indices are more likely to share similar data distribution. Second, it can also improve the performance of domain adaptation. By identifying the domain relationships, the model can better adapt itself to unseen domains, resulting in overall performance improvement. We have already discussed the advantages of inferring domain indices. The next question is how to infer the domain indices. We propose our solution here, which can be divided into two steps. First, we will rigorously define what is the domain index. And second, based on our definition, we will use probabilistic graphic model, PGM, to infer the domain indices. Let's first explore the definition. We list the definition as follows. First, a domain index should be independent of the data encoding Z. Second, it must retain as much information on the data X as possible. And finally, it should maximize adaptation performance. We summarize the three requirements as independence, information preservation, and label sensitivity. With the rigorous definition of domain indices, the next step is to infer the domain indices with PGM. The generation process of our PGM can be characterized as follows. Suppose we have n domains in total. First, we will use prior to generate global domain indices. This is 1 per domain. Here, k refers to the domain ID. Next, using the global domain indices, we generate local domain indices, which is 1 per datum. Suppose in domain k, we have dk data points, then we will have dk local domain indices. We then use these local domain indices to generate the observed data, such as an image. To provide some intuition about this generation process, I will take the gender classification task as the example again. We begin by generating the global domain indices, such as the average age. Then we produce the local domain indices, which is the age for each face shot. Based on these ages, we generate the observed data. The reason for using this hierarchical structure is that it can significantly boost the learning efficiency. With the global and local domain indices, as well as the observed data, we proceed to generate the feature embedding Z, which is domain invariant. Note that the dashed line here means beta and Z should be independent. Finally, we generate the labels for the observed data based on the feature embedding. We have also developed the inference model shown in the right figure. Now, the generating model and the inference model together constitute the complete framework. The PGM is now established, and the next step is to optimize this model. To achieve this, we will maximize the evidence lower bound, elbow. This would maximize the log likelihood of the observed data and labels. However, solely relying on the elbow cannot produce the desired domain indices. Recall that our domain index requires itself to be independent of the data's encoding Z, which cannot be achieved by the elbow alone. Therefore, we incorporate an adversarial loss to ensure that beta and Z are independent with each other. Our final objective function combines the previous two laws, the elbow and the adversarial loss. We have proved that by using this objective function, we could learn domain indices beta according to the previous definition. Specifically, the inferred domain indices will satisfy independence, information preservation, and label sensitivity. The experimental results also demonstrate the effectiveness of our model. We will use experiments on TPT-48 as an example. TPT-48 is a real-world dataset that contains monthly average temperature for the 48 contiguous states in the US. On this dataset, we will focus on transferring the temperature prediction model. One of our domain adaptation tasks is formulated as North 24 to South 24, which is adapting models from 24 states in the north to 24 states in the south. We also divide the target domains into 3 levels to report fine-grained results. Let's first see the visualization of infer domain indices. Here, the colors indicate each state's latitude. We observe that when 2 states have similar latitude, their domain indices are more likely to close along the x dimension, such as in New York and New Jersey. In contrast, when 2 states' latitude are quite distinct from each other, their domain indices are further apart on the x dimension, as seen from the Florida and the New Jersey. In fact, a correlation can be drawn between the latitude and the x dimension of the domain indices. This is reasonable because temperature is highly correlated with the latitude of the state. Notice that we never use latitude information as input. This means our model truly learns useful domain indices during the adaptation. We also report numerical results on this task. Our model achieves superior performance in both overall evaluation and final grain evaluations. To summarize, our take-home messages are as follows. VDI provides a principled way to infer domain index. It improves both interpretability and performance of domain adaptation, and it has theoretical guarantee. For more information about our work, please refer to our paper and our source code. Thank you.